Yes, sir. Singapore University assistant.
A very good morning to one and all. I welcome you all to this day 3, 1 week online faculty development program on research opportunities in electrical power engineering, organized from 23rd to 27th March 2022 by Triply Department with Prasad V. Potluri Siddhartha Institute of Technology, Vijayawada, Andhra Pradesh, and sponsored by Siddhartha Academy of General and Technical Education, Vijayawada. I welcome you all the participants as well as our today's resource person, Dr. Akshay Kumar Rathod, Professor, IEEE Fellow, Singapore Institute of Technology, Singapore. And today's topic is Power Electronic Topologies, Electrical Engineering Circuits. Now I request Dr. Nasim Prasad to introduce our today's resource person.
Good morning to one and all. I take privilege to introduce Dr. Akshay Kumar Rathod, expert in power electronics and control electrical motor drives. He received gold medal for securing highest academic standing in his master's degree among all the electrical engineering specializations at IIT Varanasi. He had doctoral research appointments with University of Wuppertal, Germany, and University of Illinois at Chicago, USA. And he served as assistant professor in Department of Electrical and Computer Engineering, National University of Singapore. And he served as associate professor at the Department of Electrical and Computer Engineering, Colorado University, Montreal, Canada, where he was listed in the Provost Circle of Distinctions in 2021. He served as graduate program director and chair of graduate awards during 2021. His research is mainly focused on analysis and design of novel current-fed converters, topologies and modulation, short switching design and modulation schemes for DC to DC converters, pulsating DC link electrolytic capacitorless inverters, and control of multi-level inverters. He supervised 11 PhDs and 14 Master of Science students. Sar is a recipient of 2013 IEEE IAS Andrew W. Member Achievement Award, and in 2014 ISAO Succeeding for Electronic Award. In 2017 IEEE PES David Erwin Early Career Award. In 2019 IEEE IAS Publication Service Recognition Award. In 2020 IEEE IAS Outstanding Area Chair Award, and IEEE Deemla Bose Award in 2020 for Industrial Electronic Applications and Energy Systems. And in 2021 Nagamori Award. He published about 285 research papers in international journals and conferences, including 96 IEEE transactions. He is currently serving as an awards department chair of IEEE Industry Application Society. AdCom member at a large and a fellow evaluation committee member at IEEE Industrial Electronics Society. He is serving as a chair of IEEE IAS Renewable and Sustainable Energy Conversion Systems Committee. He led and chaired as IEEE IAS Industrial Automation Control Committee in 2018 to 19, and IEEE IAS Technical Committee on Transportation Electrification in 2016-17. He served as a member Achievement Award Committee 2014 to 19. He served as a chair of IEEE IAS Montreal chapter from 17 to 21, and received the Best Chapter Award in 2017 from IEEE Montreal sessions for its activities. He served as a paper reviewer chair of IEEE transactions on industrial applications from 16 to 17 and 20 to 21. Editor-in-chief for IEEE IES Technology News, associate editor for various journals, that is IEEE Transactions on Industrial Electronics, IEEE Transactions on Industrial Applications, IEEE Transactions on Transportation Electrification, IEEE Journal of Emerging Selected Topics in Power Electronics, IEEE Transactions on Vehicular Technology, Transactions on Suitable Energy, IEET Power Electronics, etc. He edited 5 special issues on topics of electric transportation, EV charging marine systems, more electric aircraft, machine learning in power planning, and renewable energy conversion in different IEEE transactions is a guest associate editor and guest EIC of two special issues. He served as a distinguishing lecturer in 2017 to 18 and prominent lecturer in 19 to 21 of IEEE IAS Society. Thank you so much, sir. So, sir, you may continue the session.
So thank you, sir. That was the Now I request the first person, Dr. Akshay Kumar Rathore, sir, to continue the session, today's session.
Yes, thank you. I think it's better if the organizers can mute participants for now and unmute later. Otherwise, we'll be having noise passing through. Can you hear me?
Yes, sir.
Okay. You can hear, right?
Yes, sir. Yes, sir.
Okay. Can you see the screen?
Yeah, screen is full, sir.
Okay. Can you see the full screen now?
Full screen visible, sir.
Yes, sir, we can see the full screen, sir.
Okay. Yeah, I'm asking because sometimes WebEx and Google Meets, they have trouble. Okay. Okay, so good morning, everyone. And I would just discuss some circuit issues in power electronics, which is basically nothing but an electric circuit only, just advanced version of that. Only how do we do analysis, that is important part. Once we keep on adding components, active components, MOSFETs, diodes, or passive components, inductors and capacitor, we just make the circuit advance and for scale it up for different power levels. But power electronics overall remains an electrical circuit. Okay. So this is just outline of the presentation that will discuss classification of power electronic circuitry, that advanced version. Okay, power electronic circuitry, that it can be hard switching or it can be short switching power electronics, voltage fed or current fed power electronics. So what are the issues with them? Voltage fed has its own merits and demerits. Current fed circuits has its own merits and demerits. And for one particular specification, always a circuit is not optimized for universal application. One circuit can be good for one particular application only, because power electronics is just like a translator between source and load, right? So if this is your load and if this is source, which can be grid, which can be solar panel, right, which can be battery, and this is power electronics. So power electronics basically has to meet the source profile or source characteristics, as well as load profile and load characteristics. So one circuit cannot be good for all, because battery has a different characteristic, solar has a different characteristic, AC circuit has a different characteristics, fuel cells have basically different characteristics. Similarly, load, either resistive load has a different characteristic, right? And AC load and non-linear load, motor load, they have different characteristic. So somehow one circuit is not ideal for all. Okay, so we will see a comparison, and from the comparison you will see that by analyzing we can quickly judge which can be better for a given application. And another thing is that something that is suitable today You cannot say after 10 years that the same circuit is good for that application. No, because that is the reason that industries, they update or upgrade their technology. This is the reason behind they update their technology, because and they give it the version, different name, version 2, version 3, or new, whatever. Okay, so something the technology which is good today, after your comparison, after your analysis, selection, after 10 years that may not be good anymore. Okay, that's why the upgradation of technology is required usually at least after every 10 years. And then we'll conclude, we'll discuss any comments or questions. So power electronics is basically an electrical circuitry, and electrical circuitry is always a two-port circuit, right? Minimum electric circuit, minimum two-port, where in the circuit there is an input, right, and there is an output. This is called two-port electrical circuitry. And here what do you have? Here you have basically resistance, here you have capacitance, which is electrical circuitry. You have inductor, you have a transformer, right? You have a diode, you have IC chips, right? You have ICs, and you have switches, MOSFET or IGBTs. These all are the components of electrical circuitry inside. And two-port, minimum two-port. One is for the source and one is for the load, minimum. Right? Yeah. So what powertronics or what an electrical circuit should do? Power electronics is just a name, but it is just an electrical circuit. Okay. And that's what we have inside. Okay. So what is the objective of making an electrical circuit? What is the functionality of that? First thing is that on one port of it, we have a source. Okay. Which can be any, which can be AC, which can be DC, which can be solar, right? We just discussed, which can be fuel cell. Okay. So the purpose of this circuitry will be to accommodate the variability of the source. Suppose solar panel voltage is changing with the temperature, ambient temperature, with the solar insolation, right? The way solar insolation is changing, right? Falling on it, its output voltage changes. Based on the temperature also, it's based on the insolation, its current changes. Based on the temperature, its voltage changes. Same thing with the fuel cell. As the hydrogen flow changes, okay, the voltage and current characteristics change, right? Similarly, battery, as the battery discharge, its voltage goes down, right? Similarly, AC voltage also, we see fluctuation. It is not 230 volt always, but majority of variation comes in solar as well as fuel cells. So this is the purpose of power electronics, that whatever variation is happening, powertronics or the electrical circuit, whatever variation is happening at the AC port, your circuit should be able to manage that and process the power to the output port or the load port. Okay. Yeah. Despite the variation, circuit cannot deny that now I designed it basically for 230 volt, but the voltage has become 190. So it should not work. No, it's not like that. Similarly, suppose for solar panel voltage, you decided it for 33, but suppose the voltage has become 60 or the voltage has become 20 based on the insolation or ambient temperature, but it will work. Okay. Yes. This is first task, accommodate the variability of the source. Matching the specification. You can see here it can be, for example, 40 volt, here it can be 400 volt. Here it can be 400 volt at the input, output can be 48 volt. Suppose if it is battery charging application, then it is 48 volt or 12 volt. Input is 230 volt AC. Right. So the purpose of powertronics or electric circuit to match the specification. This side is say 230 and output is basically 48. Or input can be 48 and say output is quite large, which is say 380. So difference in specification at input and output ports, but your electrical circuitry basically will act to match these specifications. I mean, will accept it, right? Power conditioning. Input can be AC and output can be DC. It is suppose AC with 50 hertz, but output is flat DC. Right? Or input can be DC, output can be AC. right? Or input can be variable DC. Variable DC. Output can be fixed DC. So this is power conditioning, that from one form to another, alternating to direct, or direct to alternating, or variable to fix, right? This is regulation, which is variable to fix. Input voltage can change, but output voltage is always constant. This is voltage regulation. That despite any variation in the source and despite variation in the load current also changes. Suppose power is 1 kilowatt, current is, say, for example, 5 ampere. If power is 100 watt, current is, for example, half ampere. So load is changing, load current is changing. Similarly, source is also changing at the input, fluctuating, but output voltage is constant. So this job is also done by power electronics or the electrical circuitry. And power flow control, I was just mentioning that the load current changes or the load changes. Sometimes it is 1 kilowatt, sometimes it is 500 watt, sometimes 100 watt. Okay, so who will do this regulation or power flow control? The electrical circuit will do that. So the electrical circuit has these functionalities to complete the task. Okay, yeah. So whenever we do power conversion, we have to take care of these 5 objectives always. Okay, and major topic of research, one is topology, which is circuit. Topology means electrical circuit. You can design the circuit by inductor, by capacitor, by transformer, right? By diode, by MOSFET, okay, by using filters, okay, driver circuitry. These all are needed to develop a topology. So this is one topic. Okay, that is my favorite topic. In my last 10 years of faculty career, I worked majorly on developing new electrical circuitries. Okay, yes. And then the next is modulation. Many researchers, they don't work on circuit topology at all. They fully work on modulation. If you see Professor Holz in Germany, right, he comes to India very often. If you see the conference, PEDES conference, Power Electronics Drives and Energy System, he comes and attends that conference every time. If you want to meet him, December, you visit Jaipur PEDES conference. Okay, he will be there again. Throughout his life, he is one of the most famous professor in motor drives or electrical engineering. Okay, top 5, I will say, or top 3 even. Okay, throughout his life, he worked on modulation techniques. He did not work on the topologies. He used the standard circuit of 3-phase inverter or multi-level inverters, etc. But he used a different modulation techniques in order to get the high efficiency of the system. Okay, as I said that this is power electronics or this is the electrical circuitry. Okay, what is modulation? Modulation means turning the switch on and then turning the switch off. This is called modulation. In electrical circuit, once it is designed, okay, suppose once you have designed, basically inductor is fixed, capacitor is fixed, transformer turns ratio is fixed, diode is fixed, filter LC value is fixed, driver circuitry is doing its job. What you can do is only turn the switch on and off. You cannot do anything with the diode, with inductor, capacitor, filters, transformer. You cannot do anything. The purpose of the driver circuitry is to pass the signal. Whatever on and off signal you decide from your digital interface, the driver IC with protection just pass this signal. Okay, pass this signal to the switch. Okay, so once power electronic circuit is ready, only thing you can do is turn the switch on and off. And what is important, when to turn off. What should be the frequency of it, on and off? This is frequency. Okay, and what should be the turn on time? How long you want to turn the switch on, which is known as duty cycle, right? Duty cycle, which is on time divided by TS, or duty cycle is on time of the switch multiplied by the switching frequency. This is important task, and that is modulation. So from this equation, that okay, what I have to derive is the frequency or the duty cycle, which is T on into Fs, which is very simple. Okay, it is not that simple. It is not that simple. Remember one thing, if somebody asks you to develop a power electronics, what is power electronics? One is the power circuitry, right? Power electronic is basically like this, a power circuitry, okay, power processing circuitry, where inductor, capacitor, everything is there. And another part is basically a control circuit, okay, which is developing basically this on and off modulation circuit, signals basically for the switch. If somebody asks you basically that, okay, develop a power electronic circuitry, you will basically solder it very fast in one day, half day or something. But when it comes to basically modulation and control, the next step, that is the tough task. It involves basically driver circuitry design. It involves basically programming of digital interface, DSP or FPGA. It involves the calculation of on time and frequency, which is not easy. Okay, topology or circuit part is easy. Modulation and control part is not easy. First of all, you are not sure that the modulation you are going to choose, turn the switch on and off, is it really the best or optimal or not? Otherwise, this can compromise the efficiency of the circuit, because power electronics, the components I mentioned, they all are dummy component. They are a dummy component. Their performance is fully controlled by or fully governed or managed by modulation and control. The way you choose this turn on and off procedure or strategy, okay, you get different efficiency. You get different efficiency, right? Suppose, for example, for full bridge DC to DC converter, you might have heard basically several things: variable frequency modulation, variable duty cycle modulation, phase shift modulation, hybrid modulation. There are multiple techniques. Okay, which one is the best? That we have to see after comparison based on the specifications. Okay, so this is something that people spent their 50 years of life just to work on modulation. Like Professor Holz has done this. He spent 50 years of his life on modulation techniques. Same circuitry, that three-phase inverter or multi-level inverter, but different modulation techniques for optimal efficiencies for different application, right from kilowatt to megawatt. All right, for the domestic application to industry application, because things are different. You have to scale up based on the power level and specifications. Okay, another is the devices. Right, in one of the slide, I will mention you the effect of the device, but you are already aware of it. That silicon device, silicon carbide device, gallium nitride device. Right, this material is very important. Silicon devices are basically good, but gallium nitride and silicon carbide devices are better for high switching frequency. Silicon carbide devices even better for high voltage application, kilovolt, right? But silicon devices are not good for kilovolt application, but silicon carbide devices are good for that, right? Gallium nitride devices are good for high temperature applications. So now, earlier we had only silicon device, and then now we are getting basically gallium nitride, silicon carbide based, which are basically known as wide band gap devices. Okay, wide band gap devices, they can be used for high temperature and high frequency applications, as well as silicon carbide particularly is coming for kilovolt, very high voltage applications. And nowadays they are being used for solid state circuit breaker also. So material also affects the performance of your power electronics, that the devices you are using are silicon material or gallium nitride material, right? Same thing in transformer, you have different materials. If you choose a ferrite core, you will see in ferrite core also different material. PC90, PC95, N95, there are various materials, okay, based on the purity, impurity. Okay, the different core basically has a different kind of eddy current and core losses. Nowadays we are having different material. What is that? Nanocrystalline. Okay, nanocrystalline basically material for the core has basically very less core losses, as well as high density, very small core. So material also affects basically, right? Material also affects the performance, right? Yeah. So these are various topic of research. Many people, they work on only devices, packaging, device characterization, their fabrication, etc. Wafer, die size, many things. Okay. Okay, yeah, this I just discussed, that power electronics has these things inside, basically the component: magnetics, which is inductor and transformer; filters, which is inductor and capacitor; driver ICs, which is just passes the signal coming from digital interface to the MOSFETs or IGBTs, the semiconductor switches; Semiconductors, either diode or control switches. But out of those, all these components are one side. All these components are one side, that basically they are uncontrolled. Okay, but only this is the only component, okay, that can be controlled by getting signal on and off modulation technically, which basically does all the jobs: regulation, power flow control, AC to DC conversion, power conditioning, or which is matching the regulation. Everything is done by this. Okay, the other having a different purpose also, but everything is done by this switch basically. Okay, power flow control, regulation, etc. So this is quite important from the point of view of reliability. Okay, from the point of view of reliability, because if the switch fail, then the rest are not able to do the job, right? Because this is active. And why the switch fails? Switch fails because you are turning it on and off, on and off. So it has been subjected to something. There are basically dummy components. Okay, so in power electronics or electrical circuitry, two components are very unreliable. One is basically capacitor, because capacitor has its lifetime. Okay, 2000 hours, 4000 hours. So when the circuit has done, then its degradation happens and you have to replace it. Another is basically a switch, because we are turning it on and off a very high switching frequency. In 1 second, you are switching it on and off 100,000 times. In 1 second, switch is on and off 100,000 times. Okay, which is irritating to the switch. Okay, although switch is managing that, but that is irritating to switch. Switch doesn't want to do that. Switch does not like it. Okay, switch does not like it, although it is meant for that. Okay, although it is meant for that, but switch does not like it, because switching it at a high frequency on and off in 1 second 100,000 times, it increases its temperature because of the switching losses. Okay, voltage up, down, current up and down basically happens during switching transition. During conduction loss, its temperature increase. Switch does not like that at all. Then it requires cooling. Okay, but anyway, to do the job, we have to do that. Okay, so that is the only component that can be controlled, and that is called modulation. And we have to be really very careful for the switch. Many times the switch requires snubbers in order to avoid any overshoot, any undershoot, any thermal losses, any temperature rise. We have to provide heat sink, as well as we have to provide snubbers to the switch. Okay, because this is very important part of the power circuitry, electrical circuitry. Okay, we have to keep it safe in order to have the circuit reliable. Okay, we have to keep it safe in order to keep the circuit reliable. So when it comes to critical application, for example, aerospace application, electric ship or marine application, there they always purchase high quality expensive switches. They don't purchase the low quality or cheaper switches. Okay, because the important thing is the safety and reliability. In the air, in the water, there is no maintenance possible. Okay, so you cannot take the risk, because these are critical applications. Similarly, for hospital equipment, reliability is very important. That's why you see these machines in hospitals, that you see the big machines, right, for various applications for diagnosis. They're extremely costly. Okay, extremely costly, because the components used are basically reliable components. They never fail. It's like that. Okay. These are the requirements of electrical circuitry, electronics. One is better efficiency curve. Better efficiency curve means basically you want this one, flat efficiency curve, with respect to load, with respect to different source voltages. You want flat efficiency curve. For example, 96 throughout. Okay, which is not possible. Okay, which is not possible. But this is the requirement. You prefer nearly DC input current. If it is a DC to DC converter, you prefer basically flat current from the source. Okay, why? Because if it has a ripple, then your efficiency goes down, losses increase, because losses always I square R losses, where basically this I is RMS current, not the average current. Okay, so RMS current will be basically based on the ripple, and which is always higher than this flat one. Okay, RMS current of this flat, suppose if this is 5 ampere, so its average current is also 5 ampere and RMS is also 5 ampere. But suppose if it is 4 and 6, so that average is 5. This is 4 and this is 6. Then RMS current will be probably 5.2 or at least 5.15. Okay, so you will see basically that RMS current is higher than average current. So the losses corresponds to always RMS current. Okay, efficiency is also basically V out RMS, I out RMS divided by V in RMS and I in RMS. So if somehow the ripple is taken care of by the filter, that's why filter design is very important. If it is 5, then this IRMS will be 5. Otherwise, it will be 5.2. Then efficiency will be down. Okay, so proper filtering is required in order to make the current flat DC. And this current, basically the input current flat, also results into better source utilization. Okay, because suppose if it is a fuel cell, and you are supplying hydrogen, okay, so if it is 5 ampere flat, then you open the valve of the hydrogen tank to supply basically 5 current. But somehow if you have a ripple 4 and 6, so you have to basically open the valve more so that you supply 6 ampere. Okay, so basically the power is average power, the load power, which is corresponds to 5 ampere. But somehow you have a ripple. So the hydrogen flow in case of fuel cell has to be adjusted for 6 ampere. So this is a kind of loss, 5 ampere to 6 ampere. This difference, suppose for example, input voltage is 48 volt. Okay, so 50. So always continuously 50 watt loss of hydrogen, which is basically a kind of wastage that you cannot recover back. So your utilization is poor. For a better source utilization, you need a flat DC current for better utilization of source as well as for better efficiency. Okay, and somehow in power electronics, where you have these many components, okay, all these components, the current passing through this component should be minimum, so that the circuit reduce current stress, so that current passing through the circuit is through the components is minimum, so that conduction losses in the devices are less. Okay, always high current rating devices are expensive, high cost, and low current rating devices are basically cheaper. Okay, so this will result into low cost as well as high efficiency system if somehow your modulation technique can result into reduced circulating current inside the components. Okay, and one thing is, another requirement is, if your source voltage has wide variation, suppose 20 to 60, 100 to 200, as well as load variation, 5 kilowatt to 2 kilowatt, 1 kilowatt, 500 watt. Okay, can your circuitry maintain flat efficiency? Can it maintain flat current? Can it give you high efficiency throughout? This is high performance. So whenever the engineers, they start power electronics design, these are the important part, the important requirement they consider. Whenever we do our research, probably we forget maximum things. We just consider 1 or 2 points. Okay, so power electronic circuitry or electrical circuitry, they have several versions. One is isolated and non-isolated one. Means electrical circuitry without transformer, which is non-isolated. So it will have some kind of inductor, some kind of capacitor, right? Like suppose boost converter. This is electrical circuitry, right? This is boost converter. A simple electric circuitry, inductor, switch, capacitor, and diode, and this is boost converter. No transformer, right? Yeah. And isolated will come with a transformer, right? Single-ended, you have heard, single-ended is basically flyback and forward converter, right? Flyback converter, forward converter. Majority of the adapters available right now are basically flyback based.
अच्छा और the
Okay, majority of the adapters basically are flyback converter based. Those are single flyback and forward converters are single-ended converters. Okay, single-ended converter means where the current through the transformer is basically DC or unidirectional. Okay, say this is the current through the transformer like this or like this or like this. It is continuous or discontinuous, whatever, or boundary conduction. Voltage is bidirectional. Voltage is bidirectional, so that average voltage across the transformer is 0. Okay, but current is unidirectional. Current is DC. So those are called basically single-ended converters. Okay, those are called basically single-ended converter, where the current through the transformer is unidirectional DC current. Okay, a double-ended converter where the current through the transformer is basically bidirectional. Okay. The rest we will go through hard switching and short switching converter. The hard switching, short switching converter are basically classification of high frequency converters. Okay, high frequency converters. And short switching can also be implemented in different ways, either through pulse width modulation. Pulse width modulation means increasing the on time or decreasing the on time, adjusting the on and off time, or resonant converter, where we put basically resonant tank. Okay, yeah, and voltage fed and current fed converter. This is again a circuit arrangement. Okay, if you can see, this is a source and there is a inductor in series with the source. This is called current fed converter, which is a boost converter. Okay, if we develop a buck converter, how we develop a buck converter? Buck converter is like this, right? A capacitor and then a switch and then diode here, and then an inductor and then capacitor and load. So at the input there is a switch, so there is a capacitor. So when there is an inductor, what is the purpose of inductor? To have a flat current or stiff DC current, constant current. This is called current fed converter. In boost converter, you have a capacitor in parallel to the source. Capacitor in parallel to the source, the purpose is to make a voltage flat, stiff DC voltage. So that is called basically voltage fed converter. So these are just circuit arrangements. If you put a large electrolytic capacitor in parallel to the source to make the voltage constant, stiff, flat, that is voltage fed converter. And if you put a inductor in series with the source to make the current flat, constant, steady, that is called current fed converters. Okay, and the switch you have, if you switch it at a very high switching frequency, then it is high frequency converter. If you switch it at a low frequency, it is low frequency converter. High frequency converters are classified into hard switching and short switching, that we will see, as well as PWM and resonant converters. Okay, so single-ended are popular in adapter applications mainly. Okay, the purpose of high switching frequency is basically here. The high switching frequency we use in order to get compact, lightweight, and low cost system. Okay, compact, lightweight, low cost system, so that okay, so that the device, the power supply is handy. Okay, power supply is handy, very easy to ship, very easy to move from one place to another. You can carry it by yourself rather than ask for moving. It's requires very less space in at house or at a particular location, and cost is less. Okay, why it happens? Because why it happens that high frequency reduces the cost, weight, and size? Because you can see that majority of the space and majority of the cost in power electronics are taken by three components. One is magnetics, another is capacitance, and the third is heat sink. that we will see. So you can see that all these capacitors, electrolytic, when we go for high frequency switching, they are taken care by basically high frequency film capacitors. Size becomes very small. Similarly, by using, instead of using a large transformer inductor cores, if we go with high frequency, then inductor core size becomes very small, because turns ratio number of turns depends upon the core. Okay, you know already that that formula is always like this: V equals to 4.44 maximum flux, right? Frequency and number of turns. So from here you can see that number of turns depends upon the inverse of the switching frequency. Okay, suppose for example that suppose we choose a transformer turns ratio of say 1:10 for some application where input is 48 and output is say 400. So you use a turns ratio basically, say for example 1:10, just for an example. This is turns ratio, and when you start calculating, probably you figure out that primary turns comes 10 and secondary turns comes 100. So 100 divided by 10 is 10. Okay, now this is something that you decided it for example 50 kilohertz switching frequency. But instead of 50 kilohertz, somebody decided that no, I will go with the, instead of 50 kilohertz switching frequency, I want to go with 50 hertz, the grid frequency. Okay, and here the number of turns depends upon the inverse of the frequency. So this 10 turns, which was for 50 kilohertz, now for 50 hertz, this 10 turns will become 10,000, because 50 and 50 hertz and 50 kilohertz, the difference is 1000. So primary turns, number of primary turns, which was basically 10, now becomes 10,000, and secondary turn, which was basically 100, will become 100,000. So just try to think that this smaller core, EI core or this ETD core, okay, or double E core, okay, that can accommodate 110 tons of copper wire very easily. But how to accommodate 110,000 tons in a small core? It's not possible. Okay, it's not possible. This is number one. And number two is flux. Okay, number two is flux, because one is basically this switching frequency. Okay, if it is 50 hertz, then this is 20 millisecond. And if it is 100 kilohertz or 50 kilohertz, this is 50 hertz, then this is 20 millisecond. If this is 50 hertz basically, then this is 20 microsecond. So here your flux is settling within 20 microsecond, and here your flux is setting basically in 20 millisecond. Okay, flux saturation, flux setting basically. Okay, so here it is fast set, this fast setting, is basically slow setting. So here the core is basically handling the flux for a larger duration, larger timing. Okay, because of the frequency. Okay, but other places it is basically not using. Okay, so here the transformer can saturate because the flux is building for a longer time in the 50 hertz. But here the flux is basically increasing for a short time. So here a small flux a small core is good enough, but here you need a large core to sustain that flux for the flow of high flux. But here small core is sufficient because flux is basically increasing for 20 microsecond. Here it is 20 millisecond, 1000 times more. So here the core requirement becomes less already. Same thing is true for inductor. And same thing is true for basically capacitor. The capacitor value is basically inversely proportional to Fs. Higher is the frequency, smaller is the capacitance. Then probably smaller is the capacitance, one capacitor is sufficient. But if it is larger is the capacitance, then you have to connect several capacitors in series, in parallel, capacitor bank, in order to obtain the value that you want. So either one capacitor or 10 capacitors in parallel. So the size, the cost, the weight, the footprint on printed circuit board will increase. That's why we have moved, like the modern system has moved to high switching frequency. Okay. And this is heat sink, the third point, the magnetics capacitor, and then the third point is heat sink. Okay, because if switching frequency is increasing, then what is happening with increasing switching frequency? The switching losses are increasing in the same proportion. If we compare 50 hertz and 50 kilohertz, always if there is a merit, there is a demerit. Merits I just discussed, but what is the demerit? The demerit is the losses, low efficiency, because once the switching frequency increases 50 hertz to 50 kilohertz, the switching losses also increase by 1000. If earlier it was 1 watt, okay, now it is 1 kilowatt. It's like that. It increased by, because it is proportional to Fs. So earlier we discussed reduction in the size, weight, and cost. But now, again, the same thing is coming in a different way. If earlier the switching losses was 1 watt, now it is 1 kilowatt because switching frequency is 1000 times. Okay. So now what to do? 1 watt is nothing. 1 kilowatt is a lot. And to dissipate 1 kilowatt, you need a large heat sink. So you can see how large it is, 1, 2, and 3. Okay. Yeah. You can see the MOSFET, you cannot even see. Somewhere MOSFET is there. But the heat sink size is quite large because of the high losses. Probably a fan will also be required, cooling fan. So now again, the heat sink size has increased because of the higher losses, which is proportional to switching frequency. Then again, the volume has increased, the cost has increased, the weight has increased. So whatever benefit you brought by increasing the switching frequency, you lost by increasing the switching losses. Now heat sink is there, large volume, its cost is there, its weight is there. Now you lost all the benefits. Now the question is how to recover or how to maintain the benefit. Okay, although you want to go for high switching frequency with reducing the that reduces the cost, volume, and the weight. Okay, heat sink may not be that expensive, by the way. Okay, heat sinks may not be that expensive. Okay, but somehow you have to improve the efficiency, as I said, because efficiency is the measurement of utilization of the source. It is a measurement of payback period in case of solar for wind energy, alternative energy sources. Okay, it is a matter of basically meeting high energy efficiency. It should be the equipment or the appliances should be energy compatible. I mean, why is that energy star appliance, basically, where you meet some standards. Okay, so to maintain the merits of both, then researchers the work basically on source switching. So here is high switching frequency, where the switching frequency is increasing. So this transition, on and off transition and on and off losses, which was for 50 hertz before, okay, which was for 50 hertz, now it is for 50 kilohertz, right? So it has increased to 1000 times. So that you can see that the heat sink as well as the fan requirement. Okay, so its space is larger than the space of the power conversion system. Okay, so to avoid that, then source switching came into picture in power electronics or electrical circuitry. That the purpose of source switching is nothing. If you see fundamentally, what is the difference between this waveform and this waveform? Fundamentally, the difference between this waveform and that waveform is that avoid the overlap of voltage and current waveform. Because what is power loss? Power loss is basically V into I, right? But if V into I, if any one of the parameter is 0, then 0 into 1000 is also 0. Okay, so if voltage is 0, then 0 multiplied by 1000 ampere current is 0. Or if current is 0, then 0 multiplied by 1000 volt is 0. It's like that. So in hard switching and soft switching, the only difference fundamentally is that you have to avoid somehow, by some means, you have to avoid the overlap of the switching transition waveforms. Voltage waveform across the switch and current waveform through the switch, they do not have any kind of overlap, then switching losses are 0. Okay, or this is also known as decoupling. Okay, you decouple them. Okay, you decouple them. So if we are able to do that, okay, then we are able to maintain the merits of high switching frequency, or you can increase the switching frequency as much as you want, unless the switching is not compromised. Oh, sorry, the efficiency is not compromised. So here you can see compared to before, once you turn the switch on, the voltage across the when you turn the switch on, then what is happening? Earlier there was a voltage, the source voltage across the switch, the snubber capacitor or the device capacitance, which is known as COSS, of the switch was charged at some voltage, for example 100 volt. So it is discharged through the switch immediately, because switch is on, so it is short circuit, it discharges. You can see like this, and its voltage, its discharges, its voltage goes down, and the current basically increased. It may be higher before and then coming back to steady state, but there is an overlap. Same thing when the switch is off. When the switch is off, this current immediately flows through the capacitor, charging it to Vs. So this is switch is turning off, and the voltage across the switch is increasing. The capacitor is charging. This current diverts here. Okay. So this is happening 1,000 times more than 50 hertz basically. So if we avoid overlap, so how to avoid overlap? That okay, somehow first discharge this capacitor. Discharge this capacitor to 0. That's what is happening. Discharge the capacitor to 0. Then you turn the switch on. So your modulation signal should come after that, not before that. Earlier our modulation signal was coming here, and the switch current was increasing, and there was an overlap. But modulation signal or gating signal now is coming when you have basically discharged the switch capacitance to 0 first, then you are applying the gating signal to turn it on, and then the current starts increasing. The switch starts conducting, and there is no overlap. So switching loss is 0 during turn on. This is called 0 voltage switching. First voltage goes to 0 voltage, then you switch. Okay. So 0 voltage switching is associated with turn on procedure. Okay. Similarly, 0 current switching is associated with the turn off procedure. When you want to turn the switch off, what you do? You first somehow through external means naturally reduce the current to 0, or forcefully, that is known as commutation. And then after that, you remove the gate signal. Okay, after that you remove the gate signal. Okay, and once you remove the gate signal, then the current which was flowing through the switch and has gone down to 0, now it will pass through the capacitor and it starts charging it. It cannot pass through the diode because current cannot flow from cathode to anode. Okay, then the current starts, then the voltage starts building when the capacitor is charging. So this is called 0 current switching, associated with the turn off procedure. Okay, so again I want to mention after that, that's developing, designing and developing source switching converter is not a challenge. Okay, designing and developing source switching converter is not a challenge. Then what is the challenge? Challenge is basically this: maintaining source switching. You always design source switching for a particular point or for a particular range. After that operating point or after that range, the converter enters into hard switching mode again. And you cannot design the source switching for a large variation of the voltage. Say fuel cell voltage varying from 20 to 48, solar panel voltage varying from say 30 to 60, current varying from say 300 watt to 50 watt or 20 watt. For entire range, you are not able to develop the source switching. So source switching, achieving source switching is not a challenge. Okay, especially now when power electronics field is saturated in that area. Okay, so achieving attaining source switching is not an achievement, major achievement anymore. If somebody wants to do research and if you obtain source switching, any hard switching converter can be converted to source switching converter. This is general statement. Any hard switching converter can be converted to source switching converter. It is general statement. I will show you there are 3 methods to do that. Okay, but what is the challenge, or what is the research, or what is the achievement is to maintain the source switching for wide range. Input is 30 varying up to 60. Power is varying from 300 watt to 10 watt. All these load current variation and source voltage variation, you get source switching. That is a challenge. Okay, maintaining source switching. And second challenge is obtaining both. Right now we discussed 0 voltage switching, 0 current switching. Can you obtain both? No. Or if you can obtain both, yes, but for a one operating point. After that, you don't get it. Okay, so obtaining 0 voltage switching or 0 current switching for a single switch is a challenge. You cannot get both. But if you are lucky to get both, it will happen for one operating point or two operating point. Otherwise, you are obtaining only one. That's why majority of the research paper you will see are basically obtaining one. Why you don't obtain both? It depends. The answer comes from mathematics. Okay, when you do the analysis of a converter, okay, when you do analysis of a converter, then what happens? You will see the critical equations, that this equation should be satisfied in order to obtain zero voltage switching from this voltage to this voltage, this current to this current. Okay, load current. Okay, similarly, you will get a second equation for zero current switching, that in order to get zero current switching for this voltage to this voltage, this current to this current, source and load, this equation should be satisfied. Okay, now to satisfy that, you have to design LC values and all. Okay, and you will see there is not a common area or not a common overlap area of design point which can satisfy both. One is somewhere, one is somewhere. So you cannot design LC value and others in order to obtain both. Okay, this is first thing. Why we cannot do those? This is first thing through analysis. Number two, suppose you get a common area, if you are lucky, that yes, it is possible to do. But what will happen? It is possible to do both, but the problem will be that somehow it will be on the cost of increased ratings of the components, increased current and voltage rating. Okay, so you are able to get both, but suppose the current through the component head is increased. If the current through the component has increased, if the voltage rating of the component has increased, for example, then what will happen? Their conduction loss will increase. Conduction loss will increase. Then you cannot claim that compared to the traditional converter, I have developed a short switching converter, I have eliminated the switching losses. No, you did not eliminate the switching loss. What did you do? You shifted switching loss to conduction loss. So earlier it was, say, for example, 40 watt of conduction loss and 10 watt of switching loss. But right now, you have designed the converter such that switching losses has become 0, but conduction losses has become 50 or 52. Then overall losses again 50. So you don't have any merit basically. So that's what I'm saying. Achieving both becomes a challenge. Either there is no common point in the equation, or if there is a common point, it comes on the cost of increased conduction loss than before. And you cannot compromise on the conduction loss. Otherwise, you are not reducing the short switching. You are not reducing the switching losses. You are shifting the switching losses from switching to conduction. That is unacceptable. Okay. That's why attaining both is a challenge. As I said, it is possible to achieve 1 point or 2 points, but not for an entire point. But even if you can achieve one, that is good. But maintaining that one also for the entire operating range is a challenge. You cannot maintain even that for the entire range. That's why majority of the people, they work on achieving one, either GVS or GCS one, and maintaining it for wider range. So they specify we were successful in obtaining up to this. Okay. Yeah. Okay. So there are various ways to obtain it. The brilliant researchers, the genius researchers, they believe in obtaining, or they have done work in obtaining short switching using pulse width modulation, PWM pulse width modulation. Why? Because in PWM modulation, you don't need any additional components. The circuit topology remains original as such. You are only through software or digital interface, DSP, FPGA, you are basically developing a modulation technique, turning the switch on and off, such that, which is basically an example is moving from duty cycle modulation to phase shift modulation to obtain short switching. Okay. So one thing is this PWM modulation. You just discover or investigate on developing a new modulation technique to turn the switch on and off, such that the circuit can get short switching, and that for a reasonable operating range. Okay. Here you are not increasing the cost, you are not increasing the volume, you are not increasing the weight, no extra footprint on the PCBs, because you are not adding any components. So this is the simplest, most attractive, popular to the industry, and brilliant researchers work on this. But this has a demerit, that its resonance, its short switching range is limited. Okay, short switching range is limited because source switching range depends, like we had basically seen this before, right? Source switching range depends up to the point you are able to discharge this capacitor, right? As I said, first you have to discharge this capacitor first, then turn the switch on. So to discharge this capacitor has this much of energy. Okay, and suppose through PWM technique, you have some inductor, transformer leakage inductance, transformer magnetizing inductance, etc., where you are basically transferring this energy, half Li square. Okay, but this I depends upon the, this I basically depends upon the load current, right? So suppose if full load current was 100, then light load current has become 10. So this becomes small. But this is fixed. This energy is always fixed, which is half CV square, and V is basically source voltage Vs, which is switch voltage, which is always fixed. So somehow this is changing, and that depends upon the
Excuse me, somebody talking. Kindly mute that. Sir, I will mute all. Then you please can unmute it yourself, sir. One, I couldn't able to. The participants, I don't got the sound. Sir, now it is okay.
okay. So
Good morning.
okay,
Sorry, Pita. বানায় দাও ওটা তো এই দিব্যা ফোন লাগাও তো অভিষেক পোদ্দার অনির্বাণ রয় ভাস্কর রামজি দেবাশিস অবিনাশ বাপ্পা বিষ্ণু বর্ণিতা মেসেজ করো কমলি আমিও করি ফটো এটা খুললো তো বলো এই দাসে দাসে সব এক ओ नहीं ए और ओ नहीं
Oh, sorry, sir. Now, please proceed, sir.
Mhm.
এই যে দিদি নামগুলো নাও।
Okay, and next version is auxiliary transition circuitry, where generally, if you see, the majority of the work was done, auxiliary transition circuitry was in 70 80s. Okay, 70 80s, between 70 and 80, where they demonstrated that any any hard switching converter can be converted to short switching converter if we use a transition circuitry. Okay, if you use the transition circuitry. So the circuitry that we use to achieve zero current switching, that is known as zero current transition circuitry. And the circuitry we use to obtain zero voltage switching is known as zero voltage transition circuitry. Okay, and this became very popular in those 17 and 80s. Okay, this was quite popular during 70s and 80s, because this circuitry has this concept basically converted any hard switching converter into short switching converter. Okay, but as I said, that with a limited range. Okay, with a limited range. Then after that, between 80s to 90s, or even up to now, then people work on resonant converter in order to get the short switching. Okay, it became very popular, but this is not powerful for all the specification. Generally, resonant converters are popular for step down application. Step down application. And another thing is, they are popular if voltage variation in the source is not much. Okay, which is say 10 to 20% variation. If more than that, it is difficult. Okay, when it is mainly popular for Vs is high and current is basically low. Okay, and then recently, in last 5 years, 10 years, the partial resonance. So this was resonance which became popular for short switching, but in last few years, resonant impulse converter means partial resonance or short resonance. Means resonance does not happen for the entire switching cycle. Resonance happens basically for a short duration here during on, and for the short duration here during off. Means 20% resonance example, okay, and 80% PWM. It's like that. Okay, so as I said, that here it is no increase in the volume, cost, and the weight. Auxiliary transition circuitry, you need extra components on the PCB, extra footprint and cost is required. Okay, resonant converter, you need basically minimum 2 components, L and C. Okay, same for resonant pulse also, but here the pulse is basically comes for a short duration. Okay, okay, so generally resonant converter design is quite tricky and difficult. Okay, because say this is your resonant converter formula, resonant frequency formula, 1 by 2 pi root LC. And suppose you decide that, okay, my resonant frequency is say 100 kilohertz. So in order to get 100 kilohertz resonant frequency, there is an infinite combination of LNC possible. You choose L value something, you will get C value for 100K. If you increase, you decrease this. You decrease this, you can increase this. And you can get infinite number of combination. Okay, out of those infinite combination, you have to find out one. And then you have to design in your power circuitry or electrical circuitry. So to find one, you cannot find it easily. You have to do the optimization. So resonant optimization, and it is not a single optimization. It is basically multifunctional optimization. So resonant converters, only that person is successful in designing who is extremely good in mathematics, especially optimization techniques. Okay, yeah. Without optimization, you cannot do it. We will see what you need to optimize. Another thing is, although you design whatever design comes in LNC, despite anything, the analysis and control of resonant converters is relatively complex compared to PWM converters. Okay, so what you need to optimize? I've said that the optimization is needed. So what you need to optimize? One is tank kVA rating. So right now, this LNC component minimum is basically extra. This is coming extra to the converter. If its KVA rating is very high, then its cost, volume, and weight will be very high. And what is the purpose of high frequency? Cost, weight, and volume should be less. But right now, if KVA rating is high of the tank, there is volume, cost, and weight will be high. So you have to reduce it. This is number one. Number two, the gain of the converter. The resonant tank should not attenuate the voltage. If it attenuates the voltage, then you have to use a transformer with high turns ratio in order to develop the voltage. Okay. Optimize RMS current. This is the DC current. Okay. Or say this is the AC current, which is passing, say, in PWM. But resonant current should be the same RMS or something. So resonant current will be like this. So its peak and RMS a bit high. So somehow you have to optimize this RMS current, because as I said, that increase in the current will cause basically increased conduction loss. And the purpose of short switching to reduce switching loss, but not to increase the conduction loss. Otherwise, you are shifting switching loss to conduction loss side, and you are increasing the cost, weight, and volume also. So this should be optimized to be minimum, so that your efficiency can be, so that your conduction losses can be similar to before. Okay. Yeah. And all these resonant converters are basically variable frequency controller. Okay. So this switching frequency variation for output voltage regulation and power flow control should be basically a narrow range. It should not be, say, for example, 100 kilohertz to 300 kilohertz. It should be, for example, 80 kilohertz to 120 kilohertz, something like that, a narrow range, not a wide range. So your LC design, which is here, that depends upon these factors, not just one factor even. So you have infinite combination. You have to find one combination, and that one combination should satisfy this, which is not possible. So you narrow down slowly. You find out a range, then find out a value, which is a relative best trade-off, okay, to achieve all of them. Although you cannot achieve all of them with one, but a trade-off is required. Okay. Yeah. So based on the number of elements, you have many combinations: series LC, parallel LC, 2 element. Now 3 element: LCC, okay, LCC, LCL, LCL, LCLC. This is 4 element, and these are basically 3 element. Okay. And as it was mentioned here, that analysis and control is complex. As the number of elements increase compared to PWM converter, so minimum 2 components are required for a resonant tank, right? So with increase in the LC values, LC component, what is happening? Number of state variables are increasing. What is state variable? Current through the inductor is a state variable. Voltage across the capacitor is a state variable. Earlier in PWM converter, they were not there. There were only, say, duty cycle, output voltage, one inductor current. Okay. So 3 state variables were there. Now 5 state variables are there. 3 plus 2, 5. If it is 3 element, then 6 elements. So here earlier we had basically 3 by 3 matrix to solve something. Now basically you have 5 by 5 matrix minimum in closed loop control circuitry basically to solve. Okay. And solving a 5 by 5 matrix is difficult. Okay. So with resonant converter, number of state variables increase. Doing a small signal analysis of them, writing 5 equations for each mode of interval is not easy. Matrix will be large and complex, and closed loop control design will become difficult compared to PWM. So it is not just a designing the LC values. Designing to satisfy this 5 things is a challenge. And if you satisfy this, after that doing the closed loop, small signal analysis and closed loop is again a challenge. Okay, that's why resonant converters are not that easy to deal with. Finding optimal design and then closed loop part. Okay. And their major problem is they are variable frequency. If a variable frequency, then with variable frequency, it becomes difficult to design the filters, difficult to design the control circuitry. Fixed frequency control, fixed frequency magnetics are easier to deal with or design with. Okay, but large frequency variation based powertronics or electrical circuits, they have difficulty in designing the magnetics and the controllers, because controller generates a constant frequency. Okay, and there is always an error in determining the frequency for voltage regulation. Determining duty cycle is still okay, but determining frequency is a problem. You will see in the mathematical equation how difficult it is. Okay, but variable frequency in resonant converter is preferred because they maintain short switching over a wide variation. But if it is a fixed frequency, it will not maintain short switching for a wide variation with load and source. So this is pros and cons trade-off, that if you want to go with a variable frequency, filter and control will be difficult, but you can get short switching for a larger range. If you want to go with fixed frequency, design of filters and control is simpler, but you will lose short switching very soon. Okay, so these are trade-offs. Okay. Once you lose short switching, you will see efficiency start dropping. You can see this. This is the voltage, which is from 36 to 72, say fuel cell application. So you can see this is the rated voltage, which is 48, the black one. You lose short switching at 50% load, 10 to 5, 50%. You can see, and converter entered hard switching and started efficiency going down. When the voltage increased to 36, okay, this is more or less good. Okay, when the voltage increased to 72, you can see after 80%, it lost short switching and efficiency is going down. As I said, first of all, flat efficiency is not possible because of the switching losses in high frequency converters. But when the operating voltage changes from 36 to 72 or 48 to 72, you can see it loses short switching even very fast. Okay. So somehow obtaining flat is a challenge, even if it is short switching, because short switching is for a particular range. It is not short switching for the entire operating range, as I was saying. It is a challenge. And even maintaining both maintaining one is a challenge. Not even both, but maintaining one is also a challenge. Okay. Okay. So when we design this short switching converter, okay, so you can design it for voltage fed, you can design it for current fed. So voltage fed, we just said, what is voltage fed? When there is a large electrolytic capacitor in parallel to the source, so that voltage across the power converter is flat DC. This is the power converter, right? From here, switches up to here. This is source, this is load. This is power converter. So between source and power converter in parallel, there is a electrolytic capacitor. Large electrolytic capacitor, so that voltage across the power electronics is flat DC. So you can see everywhere it is there. So this is full bridge, half bridge, push-pull combinations, push-pull topology. Okay. Now, what you want to place at the output? There are two possibilities. So this is just electrical circuitry. You can see the switch, just advanced because more switches, a transformer leakage inductance, filter, diode rectifier, right? Like that, electrical circuitry. So now two things. One is what you want to put at the filter, at the load. Either only capacitive filter, or you want to put basically inductive filter. So this is inductive filter and this is capacitive filter. Okay, so performance is completely different. The operation is different and performance is different when you put electrical, or when you put basically, when you put capacitor and when you put inductor, the performance is completely different. Okay, you can see if it is a capacitor, then what happens, that here also capacitor. So a voltage source, okay, which is available here. This is, and here is basically inductor. So a voltage source, an inductor, and the output side also a voltage source capacitor. Okay, so delta V. So inductor current will rise like this ramp, which is L di by dt. L di by dt equals to this delta V. So if this difference is large, then the peak current will also be large. So in capacitive filter, the problem is basically high current passing through the converter, peaky current. And this current will be higher if this delta V, the difference is higher. Okay. And in case of inductor, because inductor is there, so output current will be flat, I naught. If this is I naught, then by this turns ratio, this current will be I naught by N, which is flat, like this. I naught by N minus I naught by N. After rectification, it is I naught, I naught, I naught, I naught after rectification, right? So here lower peak current. Okay, lower peak currents. So here capacitive filter are preferred basically for low current application because it is peak current. So 5 ampere average will be basically 10 ampere peak. But if it is say 50 ampere, then it would be 100 ampere peak. So which is not preferred basically. Okay. So this is the problem in capacitive filter, higher peak currents. Okay. But in inductive filter, this is not there because of the inductive filter flat current, but it has other problems. Other problem which is called duty cycle loss. So once we change the filter, either inductor or capacitor, we get basically different merits. Okay. Or demerit. One is called duty cycle loss. What happens? What happens that right now, say for example, this current is 10 ampere flat here. Say turns ratio is 1:1, for example. So this is also 10 ampere. This is 10 and flat is 10. Okay. And here you have an inductor. Okay. So suppose this inductor is carrying this flat 10 ampere current when this pair is on. Now after half cycle, half of the switching cycle is over, TS by 2. Then this pair is on. So the current has to be negative in the opposite direction, bipolar. But because of the inductor, LDI by dt, this current basically will change slowly. It will not change like this flat, not like this. It will basically change. Like this. So here and here. So this is 10 to minus 10. So there is a transition period that depends upon two things. One is delta V and another is this leakage inductance value. If higher is the value, higher is this transition time. If lower is the value, lower is the transition time. Okay. So you can see now there is a difference in the current. So this current was 10, then this was 10, it was matching. So 10 ampere current is passing here, 10 ampere. Now this is 9. So how this 9 ampere current is 10 ampere current now? It cannot be. So there is a mismatch. So because of this mismatch, all the 4 diodes start conducting in this inductive filter. How does it happen? How does it happen? Say what happens that whatever the difference is. Okay. So earlier DR1 was taking 10 and DR4 was taking 10. Okay. DR1 and DR4, they are basically carrying 10 ampere current and the other two were basically carrying 0 ampere current, DR1 and DR3. Sorry, DR2 and DR3. Okay, here and here 0 ampere current. Now the difference between the primary side and the secondary side, the difference of the current is shared by the remaining diodes. What happens that the sorry, this is DR1. Yeah, this is DR1 and DR4. Yeah. Now what happens that the difference of the current is shared basically by this. Means whatever this difference has come from 10 to 9 in the primary side, which is basically 1 ampere. So what happens that DR1 and DR4, its current will reduce by half of the difference. And DR3 and DR4, which was off, its current will increase plus by half of the difference. And its current will be minus by half of the difference. Half of the delta I. Means suppose this was 10 before. What the difference? Say this is 10 and this is 9. So the difference is now 1 ampere. So DR1 and DR4 will carry 9.5 because difference of 1 by 2 of 1 ampere is half. So 10 minus half is 9.5, and they will carry basically half ampere and half ampere. So you can clearly understand. So this was this is 9.5. This is 0.5. This is 0.5, and this is 9.5.
And say that at last you can answer.
And this is basically 9. So you can see this is 9 ampere, and the 0.5 is coming from here, will become 9.5. That's what we said. This 9.5 is here. From this diode, 0.5 is coming. 9.5 and 0.5 will become 10 ampere. Okay, this 10 is passing here and divided into 9.5 here and 0.5 here, satisfying the Kirchhoff current law. And when it becomes 8, this 10 becomes 8, then this DR1, DR4, they are carrying 9 ampere now. 9 ampere, and they are carrying basically 1 ampere. So you can see 8. So this is 8. 8 plus 1 is 9. 9 plus 1 is 10. And this 10 is divided 9 and 1, satisfying the Kirchhoff current law. So that's how the current sharing happens. And this current sharing is turning all the diodes on. If all the diodes are on, then there is a short circuit across the transformer. If there is a short circuit across the transformer, means there is no power flow from source to load because secondary voltage is 0. Okay, so this is called duty cycle loss. You can see that the voltage across the secondary is 0, although voltage across the primary is not 0. This is called duty cycle loss. And this duty cycle loss is basically because of the transformer leakage inductance. Higher is the leakage, higher will be the duty cycle loss. So since the voltage loss is happening, then you have to increase the transformer turns ratio to meet the output voltage demand. Okay, to meet the output voltage demand. So once you decide that, okay, I'm using the inductive filter in my circuitry, if you decide, the first thing you need to do is minimize the transformer leakage inductance in order to avoid this duty cycle loss, as well as in order to avoid the rectifier diode ringing. Each rectifier diode has a capacitance of the order of picofarad. And if this picofarad basically resonates with microfarad, okay, you will see this gigahertz switching frequency that increase the voltage across the diode rectifier twice of the normal voltage. Okay, twice of the normal voltage. And this twice of the normal voltage will require basically double the output voltage, double the voltage rating of the diodes. Okay, which has basically higher conduction loss as well as cost will be high. Okay, you can see higher resistance and cost will be high, or you need to put basically snubber capacitors. Yeah, sorry, snubber resistance across them, RC snubbers. Okay, so because of this reason, inductive filter, as soon as you decide that, okay, in my converter I will go with inductive filter, the first thing you need to do is you need to minimize the transformer leakage inductance as much as possible, minimum, so that you avoid these issues of duty cycle loss and rectified diode ringing. Otherwise, there is a significant drop in efficiency and increase in the transformer volume, size and volume. Okay, yeah. Current fed converter gives you many benefits. One is short circuit protection, because current fed converter, it is in series. The inductor is in series with the source, so it gives you short circuit protection. And since this is a boost converter, okay, it is a boost converter, so output voltage is basically higher than the input voltage. All right, so it can be 10 times high, and because the inductor limits the current, so it will limit the current to basically, unlike resonant converter where peak current is double. All right, and inductor is reliable than capacitor, because capacitor has a limited lifetime of 2000 hours, 5000 hours, but inductor material degrades over time, its a value will go down, but is reliable, it does not fail. Capacitor fails, but inductor does not. Okay. Okay, but these were the merits. But what is the demerit of current fed converter or boost derived converter? That when you turn the switch off, this inductor current which was flowing cannot be interrupted. and this current cannot pass through the transformer inductor instantly. Okay, because inductor property is that inductor opposes the change in current. So transformer current, whatever it was, 0, 5, whatever it was, it will not increase from 0 to whatever it is, or whatever value it was before, it will not increase from that instantaneously. So the current which was flowing through the switch cannot divert to the transformer immediately, cannot go through the diode, cathode to anode. So it will go through the capacitor, and it will charge the capacitor, because this inductor current has to flow somewhere. And capacitor will rise, voltage overshoot, Li square try to convert into CV square, right? So this will damage the switch. Okay, so that's why current fed converters are known for two things. They cannot be commutated easily. Okay, they cannot be commutated or turn off easily, or they require snubbers. Okay, or they require snubbers because of this high commutation turn off voltage spike. Okay, so over time people use different snubber. The easier one is RC, so it started with RC. Okay, later on RCD, different format, all right, different way up to inductor. Okay, and active clamping. What happens, the current when the switch is off, here the problem is that current cannot pass through the cathode to anode, but here this current, inductor current, immediately pass through the diode and then charge this pre-charge capacitor. So when it passes through the diode voltage is 0. So what is the switch voltage? Switch voltage is same as this capacitor voltage, and switch voltage is clamped rather than voltage overshoot. So this is called active clamping. You are using another switch to clamp a switch. Okay, so the current passes through the diode instantaneously and goes to the capacitor. Okay, so this is short circuit. So by Kirchhoff voltage law, what is the switch voltage? Switch voltage is the capacitor voltage. Okay, and after some time, after half of the switching frequency, you turn the switch on in opposite direction so that this capacitor discharge. So suppose earlier capacitor voltage was 100 volt. During this charging time, it will increase to say 105 volt, and during discharging through the diode, this is through the diode, then the switch is on, it will discharge back to 100 volt. Now switch is conducting, and then that's it. Then again charge, discharge during switch on and off, and then that's it. It's like that. So this is the switch voltage, this is the capacitor voltage, and this is the switch voltage. So capacitor voltage will be clamped by using active clamping, and this was the most popular up to 2010. But the problem is solved, but you can see that is increasing the extra footprint. The originality of the circuit is compromised of current fed circuitry because of the snubbers, and it has taken extra footprint, extra space on the printed circuit board, power processing circuitry, causing the volume, cost, and weight. Okay, and of course it is not preferred by the industry. Okay, but they have taken the place. Okay, and one thing is that this was a boost converter, and because of this active clamp, power is basically interrupted for some time. Okay, and because of this V in upon 1 minus D, the extra term is coming here that basically compromises the boost capacity. Okay, that compromises the boost capacity of the converter. Okay, so the way we have a current fed full bridge using one inductor, entire current I in is following, and here the input current is divided half, I in by 2 here and I in by 2 here. It is half bridge converter, and you can see when, so now there are two inductors, so there are two active clamping circuit. So when this current was flowing through this switch, when the switch is off, this current flows through this diode and goes to the capacitor, and then it discharges through this switch and goes to the transformer. Similarly, when this switch is off, this current flows through this diode and this switch, and when it is discharges through this switch, come through the transformer. Okay, but again, boost capacity is compromised. So in half bridge, or we can say higher is the number of inductors, higher is the number of switches, active clamping switches. Okay, so in full bridge it was 1 because 1 inductor. In half bridge there are 2 inductors to divide the current half and half and process to the power processing circuitry. So it is basically two switches are there, one for this inductor current, one for another this inductor current. Okay, so just this circuitry that we discussed, the voltage fed PWM converter, voltage fed converter with capacitive filter, with inductive filter, and current fed converter. If we compare them, for example, all are electrical circuitry. Only the difference is capacitive filter or inductive filter. For example, you can see LC series resonant converter, full bridge, voltage fed. Voltage fed, you can see no inductor, LC resonant, and capacitive filter. The same circuitry now, voltage fed full bridge, LC resonant, but inductive filter. Very minor change. Okay, now instead of C, this C has been eliminated. So it is voltage fed, but no resonance. Now it is PWM. C has been eliminated and inductive filter. Okay, now instead of inductor, capacitive filter, no resonance. Okay, no capacitor, voltage fed. So voltage fed PWM with capacitive filter, voltage fed PWM with inductive filter, voltage fed resonant LC resonant with inductive filter, voltage fed resonant with capacitive filter. And here is PWM active clamp that we just discussed, capacitive filter. No need of inductive filter in current fed because inductor is already there. All right, at the input side, either full bridge or half bridge at the input to limit the current. So we don't need inductive filter, only capacitive filter. Okay, so if we analyze all this converter with minor difference, right? The first four converter, not much difference if you see, right? Instead of capacitor, here is an inductor, same converter, right? Just remove the capacitor. Okay, inductor is there. Now remove the inductor, only capacitor is there, and one active clamp current fed converter. Okay, now say it is for fuel cell application, where as the fuel cell, what happens at light load voltage, fuel cell power is less. Fuel cell power is less, but voltage is high. And when you load it further, then at full load power, the fuel voltage goes down. Say, for example, this is 22 volt, and say this is 48 volt. Several fuel cells So we designed the converter for this variable voltage, maximum rated power of 1 kilowatt, output is 350 or 380 volt DC bus, and switching frequency of 100 kilohertz. Okay, now you can see the same circuitry with minor variation, capacitor and inductor. You can see how the performance, same converter with L filter or C filter, or PWM with L and C filter. You can see their leakage inductor design comes differently. PWM inductive filter design becomes unrealistic, like 0.1 micro, which is not very easy to design, which is very difficult. Okay, current fed is 1 micro, which comes the most realistic. Okay, which comes the most realistic. The others are still okay. 500 is quite okay. This is also quite okay. This is a bit unrealistic, but still okay. But you can see that PWM converter with L filter cannot be designed for high power application if your specifications are like this. If suppose right now I put 1 kilowatt, if I put it 2 kilowatt, suppose, then this 154 becomes basically 0.77 micro, 0.077 micro or 77 nano, which is not possible at all. Completely not possible. Okay. So first of all, that which converter design is realistic, that itself becomes a challenge when voltage variation is quite large at high switching frequency. And if it is a step up application, 22 input, 380 output, almost 18 or 19 times of gain is required. So with high voltage gain, with high switching frequency, with a step up application, with large variation in voltage, power transfer design or circuit design is a challenge. It's not realistic sometimes. Okay. After that, if we compare their performance, you can see this is for 22 volt outside, and inside the bracket is for 48 volt. So you can see in resonant converters, especially capacitive filter, the current increases. Although the voltage is increasing, so current should decrease from 22 volt, which is outside. The current inside is for 48 volts, so it should go down. But you can see it is going up. Same thing here, you can see voltage fed with C filter. Earlier it was 66, now it is 127. Inductive filter, because of the current limiting feature, it is more or less same. But it should decrease, right? Because voltage increases, so it should decrease, but it is more or less same. So this is peak current. Forget peak current. Important thing is switch RMS current, which is responsible for the conduction loss. So you can see in inductive filter, it is similar, 40, 40, 36, 36, 37. Okay, but you can see in capacitive filter, the voltage increased from 22 to 48, so current should decrease, but instead of 38, now it has become 51. Earlier it was 41, now it is 47. In inductive filter also, when voltage increase, current should decrease, right? But it is similar. But if you see current fed converter, earlier it was 29, it has not become half, but it has reduced to 18. It is not 15, but it is 18. Since the current fed converter has a voltage gain, so you can see its turns ratio is 4, but the rest is 16 to 20. Okay, so you can see how they are performing differently. Okay, because of increased current, because of the increased current, or more or less same current, you can see the conduction loss has increased. Earlier this was for conduction loss for 22 volt, this is for 48, although it should be down. Here you can see more or less same because current was same. Here is more or less same because current was same, although conduction loss should decrease with the decrease in the current because voltage has increased, but current didn't decrease, so conduction loss didn't decrease. And here, because of capacitive filter like this, you can see it has increased. But in current fed converter, you can see the RMS current has gone down, so conduction losses had decreased. So you can see because of conduction loss increase, you can see efficiency. Say it was 88, for example, now it is 80. So there is a 8% difference in efficiency when the voltage has changed. Here it is more or less same, more or less same. Here it is also 3% change. So you can see in PWM C filter, the efficiency difference comes to be 3%, but it comes to be 8% in resonant converter. Because resonant peak current is quite high, its RMS current is quite high, and it does not decrease with the change in the voltage, with the change in the load current. It doesn't change. This is the major disadvantage of resonant converter, that with the decrease in the resonant current, with the increase in the voltage, with the decrease in the current, load current, it does not decrease. This is the major disadvantage. Okay. Yeah. But current fed converter, because the conduction loss already low, then with the increase in voltage, it has become further low. So you can see there is an increase in 5% increase in efficiency. Okay. So as I was saying, that depends upon the specification. Different circuit shows different thing. And there is not a major difference in the circuitry. Either one inductor is extra, somewhere inductor is not there, capacitor is extra, somewhere there is a capacitor is used for resonance, somewhere it is not used. That's it. Minor changes. Right? So this was basically in 2006 or 2007. And this was now in 2017, 5 years back. I did one more time. So that's what I was telling you, that the technology today is the best, the topology or the modulation, the circuitry. You cannot say it is the same after 10 years also. So here I have basically based on the available devices in 2006, MOSFETs, diodes, transformer material, this analysis was done. After 10 years, based on the devices available in 2016, for example, Infineon Optimos, I use the diodes. I use basically Infineon Optimos on the primary side, MOSFET, Infineon Optimos. I use basically nanocrystalline core transformer to reduce the switching loss. And I use basically silicon carbide diodes on the secondary side to reduce the reverse recovery and anything. So you can see earlier the losses, which was 118 and 215, with the new devices has become 36 and 64. You can see 118. So it is almost double approximately. So losses is double still, 36 to 64, it is double. The ratio remains the same, but the number has gone down. You can see here it was 128, 123. It is same. Here it was 104, 114. So it is 31, 34. Here it was 139, 177, less than double. Here it is less than double. Okay. Current Fed, which was 89 and 34. Now it is 30 and 11. This is for half bridge. Now I added for full bridge also. More or less similar, doesn't change much. So now you can see the earlier where the difference in efficiency was 8%, minus 8%, right? And the highest was 87 and minimum was 80 and difference was 8%, right? 80 and 88. Here you can see that the difference has become now 2% and it is 92 and 90. Here it is same because inductor, so more or less same, which was 85 before and 87. Now it is 91 and 92. More or less same in inductive filter. Here the difference was 5%. You can see, and it was 85% efficiency and 82. Now it is 92 and 90, above 90, but instead of 5%, now only 2%. Here it is approximately 2.85 or say 3%. Okay. And here you can see where the increase was 5% increase. Now you can see the increase is only 1.5% increase. Because saving is not much. Losses has become less, but saving has become less. So now earlier there was a quick selection that, okay, go for this topology. But now go with any topology. Okay, although still you can see current Fed is better because as the voltage increasing. But you can see for other application where the input voltage variation is not this much, probably 10%, then you can go with number 3, PWM with capacity with inductive filter. 92.2 and 91.8 doesn't make any difference. Or you can go with first 92.85 and 90, doesn't make much difference. If voltage variation is right now too large, instead of suppose 48, if it is 22 to 33, then probably it is 92.85 and 91.85 probably. So it's flat. So you can see that after 10 years, the semiconductor devices, that was also one of the research topic I mentioned. Okay, so you can see that efficiency is more or less similar now, and comparison is not a quick, but it's very difficult to make it. Okay, so in addition to the circuit component, the device itself can change the performance of entire power converter. Okay, and source switching part, you can see all these converters, either it is resonant or PWM, they are losing source switching because it was not designed for such a wide operating range. If you design for wide operating range, as I said, conduction loss will increase to reduce the switching loss. So all these converters lose source switching at light load or with the increase in the input voltage. Okay. Okay, so I had taken enough time. So I will be happy to answer any questions.
That's a great presentation, sir, on the different converters, converter topologies, and the performance also with respect to various device elements. Thank you very much, sir. So I request the participants to, like, whatever the questions you are having, like doubts regarding the topics, you can ask, sir. Request the participants to kindly share your feedback as well, your clarifications in your chat box, or you can unmute your mic and clarify. Sir, a few questions in chat box, sir. Sir, a few questions in chat box, sir.
Okay. Uh, so what will be if switch 1 and 2 are replaced with inductors? Will it be voltage fed converter or current fed converter? Yeah, so that becomes basically half bridge current fed converter, the topology that I mentioned later. So that voltage fed, where we had four switches, and the top two switches we replaced by two inductors. Current is dividing half and half, so it becomes current fed converter. Any switching device available with low turn on voltage less than 0.5 volt. So generally the chip level power electronics, where the voltage rating is quite low, less than 10 volt or 20 volt. They have basically low turn on voltage and low RDS on also, the chip level power electronics. Yeah, only these two questions are there.
Yes, sir. Any more questions from the participants?
Interleaving concept means basically multiple cells or multiple modules that are sharing the current in order to increase the power level with the reduced current rating devices. So interleaving means suppose input current is divided half and half or 1/3. If you have three cells, then 1/3. So they share the current so that you can scale it for high power. So suppose earlier suppose this half bridge converter or this full bridge converter we mentioned, say this is enough for say 1 kilowatt, then you can have three cells or three modules in parallel operating for say 30 kilowatt. Okay, so it is just for the scaling of power by sharing the current. Voltage remains the same. Current is basically 3 times if three cells are interleaved and sharing. If two cells are interleaved and sharing, then it is double the output power. You can also unmute and ask question actually. You can unmute the participants now and they can ask questions also directly.
They can unmute, sir. They have an option to.
Good afternoon, sir. Sir, myself Nitesh Kumar, and I want to ask one more question. Basically, whatever current fit topologies we used to see in papers and research works, they generally used to use a capacitor type of filter in the output side. Is it some restrictions or that is the most preferred one? That means why not inductor or filter are generally chosen in those current fed type of inverters?
Look, in current fed, you don't need inductive filter because inductor is already there. So capacitance is enough at the output. That's what I was explaining, that in inductive filter, you already have the current for limiting the current values.
But
so you don't need basically another inductor at the output.
In the output side, diode bridge is there, and that will be producing ripples in the output current. So there.
But diode will not produce ripple. The diode is just passing the input current to the output. It's just rectifying. It will not adjust the current values.
Okay.
Yeah, diode will not adjust any current actually. It is just rectifier part.
Due to some this LC ripple and other things.
Where LC?
And that inductor and diode diode body capacitor.
No, that will not cause because it is capacitive output filter. So in capacitive output filter, the resonance will not come into picture. LNC, it comes into picture in inductive filter only.
Okay, sir. Thank you, sir.
Any other participants?
Yeah, am I audible, ma'am?
Yes, sir. Yes, you are audible.
Okay, thank you, sir, for your wonderful lecture. So you covered from the basics to advanced topics. Sir, so just I wanted to know what are the applications of this current fed converters, and Second one is, can we use this current fed converters for the bidirectional operation?
Yes, yes. Current fed bidirectionals are also there. I mean, if I can share some slides.
Any other questions from
So I'm
participants?
just trying to
I
see
think
current fed. Sorry, this is why I'm not able to share probably again. Yeah, here. So if you see, you can see this is bidirectional one. So they have bidirectional topologies, current fed bidirectional. Here it is another one. This is full bridge bidirectional. So generally voltage fed has just capacitor here, and bidirectional. And here it is inductor one side, capacitor another side, and bidirectional.
Okay, thank you, sir. Sir, one more question. In dual active bridge in voltage fed, mostly we'll talk about ZVS only, right? But when it is in current fed, we'll talk about ZCS operation. Am I correct?
Generally a ZVS.
As per the literature I'm talking, mostly in your papers also you will talk only ZCS.
Yeah, I talk
right? So
ZCS
why it's so, sir? Just to know
because
curiosity. Just
because current fed the requirement is ZCS. Because if you see, when I started current fed, I mentioned the problem of current fed is basically commutation, turn off. So if you can make the turn off smooth, soft, zero current turn off, then you get rid of the problem of voltage spike. That's why we choose DCS.
Okay. No, my question is just why we'll not why will in voltage fed mostly we'll discuss about ZVS, whereas in current fed we'll discuss about ZCS. Is there any reason? I understood from your point of view this.
So
Can
ZCS
you please give yes, please.
ZCS we prefer current fed because of its problem of turn off voltage spike. Turn off is hard. So to make it smooth and remove the problem of spike and snubbers, that's why we use ZCS in current fed. In voltage fed, you do not have this turn off problem, and zero voltage switching basically offers you more merits, because if turn off is hard, then what happens that you need RC snubbers basically. Sorry, if turn on is hard, then you need RC snubbers basically. And in MOSFET, basically, you do not have any problem of turn off voltage spike. So to leverage upon additional merits, they prefer zero voltage switch. In current fed, we are just solving the problem of snubbers. That is the major goal. In other things, we are not taking care that you do in the voltage fed converters. So GVS in MOSFET is always more beneficial compared to GCS. That's why they go for zero voltage switching. Turn off as well as no RC snubbers, because there are no turn off issues. So it is just a original circuitry as it is.
Okay, thank you, sir. One more question. Sir, generally, when we are talking about high frequency operation, we'll go for MOSFET, right? Suppose if I have application,
can go 150 kilohertz also, IGBT.
Yes, yes. Sir, suppose if I have application, it is very high power. Okay. So high power and we need isolation also. Okay. So in that case, what is the devices we will prefer? High power, we need high frequency operation also.
For what application?
With powertrain.
Oh, electric train, you mean?
Yes, sir. In electric powertrain, I have seen some papers. Actually, generally,
powertrain is something else. That's what I'm saying. Powertrain means propulsion circuitry. But for it is electric vehicle or it is for railway?
Electric vehicle.
Okay. So there basically the inverter switching frequency is low. Inverter switching frequency is not high. The propulsion inverter 10-20 kilohertz because of hard switching. So there they use IGBTs.
Now I'm talking about DC-DC converters.
Yeah, DC to DC you can have high switching frequency with MOSFETs.
And it is when it's operate high power also.
That is fine.
Both
That is
requirements are.
That is fine. MOSFET can manage. Yeah.
Okay. Thank you, sir. Thank you very much.
Thank you very much, sir. Such a wonderful presentation, and also like the clarifications what you have given, I think might have reached our participants. Thank you very much, sir.
Thank you.
Thank you, sir. So I request the participants to stay back because we are having a session at 2 o'clock. The feedback link is enabled in chat box. So all the participants can fill the feedback link, and the next session will be at 2 o'clock. Actually, today, sir, so as we have to start at 11:30 based on our resource person's request, so we had to continue, sir, till 1:30. So we'll be shorting at 2 o'clock, sir. So request the participants to stay back in the same link so that the session will start within 10 minutes.